in some examples like free scalar, free fermions, and some short flow generated by some weakly relevant deformation. And then I will speak about some future directions. So let me start with reviewing this conformal anomalies or the trace anomalies in 4D CFTs. So let's start with a conformal invariant, or I think we should talk about like while invariant some quantum field theory in 4D card background. And suppose this while invariant QFT has an action with some fundamental degrees of freedom with some fields, and we put it or conformally coupled it in background card space-time. So under while transformation, let me define the while transformation. The metric scales like and suppose this fundamental degrees of freedom also scales some way, which is not important. And the claim is that in a while invariant theory, our action is invariant under this while transformation. Now, starting with this action, we can try to define a connected functional by integrating out my QFT degrees of freedom, which is defined as function of only the background degrees of freedom, which is the metric, which is the classical background. And we integrate out, suppose, the QFT degrees of freedom in card background. As you know, most of the times we won't able to find a measure of the path integral which is both diffeomorphism invariant and while invariant. And that's it. That is why, though this action is while invariant, usually we get that this connected functional is not while invariant. That is the source of the anomaly. In a sense, you can try to think like some Pataviti example. What happens is that in general, when you try to do this path integral, you will find some UV divergence, and then you need some counter term to regulate it, and basically you won't come up with some counter term which is both diffeomorphism invariant and while invariant, and that is basically the source of this while anomaly. And let me define the infinitesimal variations of this connected functional. And it turns out that due to this while non-invariance of this measure, it is non-vanishing. And for a while invariant theory, people already constructed what will be this form of this variation of this connected functional. And as you know, it is basically related to the trace of the stress tensor, one-point function in card background. And since it's a dimension 4 object, like scalar object, we have to construct out of the metric. And since while invariance is like a kind of a, it's like abelian symmetry, so you have to use the Weiss-Domino consistency condition. And one finds that it can be written as only in terms of 2 unknown coefficients and a combination of scalar curvatures. This E4 is the 4-dimensional Euler density, which is in general, it's a topological term, and which is like square of curvature tensor. One can write its form, and this is like the Weil tensor square. In general, one can write some kind of box of R term as well, but that we can work in a scheme by adding some R square with proper coefficients with this action to get rid of this term. So this is known as this Weil anomaly or trace anomaly, and this coefficients A is known as this A anomaly coefficients, and this is known as the C anomaly. And my primary interest today is basically describing how this C anomaly flows along the RG flow and how can we probe it using some kind of amplitudes or vertices. Okay. So before going in details, let me try to explain what is the difference between this A and C anomaly in general. You can see if I put this Weil transformation parameter to be a constant, which basically turns out that it's related to some just a scale transformation, then you can see since E4 being a topological term, like it's becoming a boundary term and it vanishes with proper boundary condition, and only we are left with this Weil square term. So that's why C anomaly is known as also the scale anomaly, which is also known as this type B anomaly as well. On the other hand, A anomaly is this famous like generalization of the 2D conformal anomaly. And this, we know, this A anomaly has, like, it's basically flows monotonically along the RG, like it changes monotonically along the RG flow. But this C anomaly coefficient, which is the scale anomaly, like it don't have any kind of monotonicity property, even there are counter examples. But if we try to characterize a CFT, like it will be interesting if we can find some bound on these coefficients, then we can able to kind of put some bound on the space of CFTs. And this is the goal, and to do that, we first need to find an observable which can probe this coefficient. This is kind of the motivation. So at this point, is there any question? Yes?
So with the bound on the A anomaly, you're excluding all flows that would come close to your UV fixed point. But right. With the C anomaly, you're not, right? Because it's not monotonic.
That's true. So but yeah, like the kind of way we can treat, like suppose this, there is some UV CFT and we deformed, and suppose it always gives some kind of massive QFT, so that the IR fixed point is like some empty theory. In that case, we can able to, because we know that this C have to be positive from the unitarity of CFT, but we can able to put also some bound assuming some QFT like massive degrees of freedom as well. So this is kind of one way to probe a CFT. Okay, so in general, like people have also in past also constructed this connected functional, whose variation provides this A and C anomalies, and I will just schematically write its forms, like corresponding to A anomaly, the connected functional have this kind of non-local action. And some other terms also in the order of curvature cube. On the other hand, the connected functional associated with the C anomaly will have the form this W is again this Weil tensor square. Okay, so from here, one thing is clear. If we like use like the diagonal subgroup of deep cross Weil and try to see like the conformal field theory in the flat space-time, then basically if we start with this connected functional and expand about like flat background with like G mu nu to be eta mu nu plus 2H mu nu, you can see to probe the A anomaly, we need 3-point stress tensor to compute. On the other hand, if we want to probe the C anomaly, 2-point stress tensor is enough, because I can expand this Weil square and I can only I can probe this C anomaly coefficient in a CFT at order kappa square, or the two fields H mu nu. So this is kind of a difference in terms of this connected functional as well. And one can see in a 4D CFT also that if one computes the 3 stress tensor correlator, it has 3 different tensor structure with some OP coefficient, and the combination of OP coefficients both contains, this 3-point stress tensor contains both A and C. On the other hand, one can compute also 2-point stress tensor, and which is given by some central charge with some tensors proper. And one can able to see actually this central charge, which appears as a combination of OP coefficient in the 3-point stress tensor. One can relate it to the central charge CT, because one can use in a the CFT word identity to relate it. So that is why this C anomaly coefficient can be read of both from 2-point and the 3-point stress tensor in a CFT. In general, there is a precise relation between them. With this choice of normalization. Okay. So now with this information, we can ask this question that, like, what is known about this C anomaly? Is it known, like, do we know any kind of bounds? Already people have derived some kind of at least some kind of sum rules or some kind of bounds in a CFT, and let me try to review a bit what is known. Okay, so first of all, since C is proportional to this CT, you can use unitarity of the CFT, and obviously this C anomaly in a CFT always is greater or equal to 0. Okay. Then another interesting proposal is given by Gilios, Liu, and Luti. What they started with, they put a like conformal field theory in curved background, and then they use like this 4 graviton pseudo amplitude. In a sense, they just scattered 4 gravitons, the part of the graviton amplitude which contains only the 4-point stress tensor, and then they use the OR identity follows from this relation and some complete set of bases in a CFT using this OP expansion, and they found a sum rule for the C anomaly, which has this kind of form, the operator which appears in the OP expansion of the stress tensor, and this is without the identity and the stress tensor, because the identity is from the disconnected part of the amplitude, and the stress tensor can be absorbed in the right hand side because it appears also C, and they have given a formula for it in terms of the OP coefficients of the TTO operators and some positive function which is completely fixed by conformal symmetry. And from there, one can also able to see it's positive. And more interestingly, if one can do some numerical like conformal bootstrap and can find some bound on the CTTO coefficients, from there one can able to see, or one can able to bound the C coefficients in a CFT as well. But somehow no one did stress tensor correlator in 4D like bootstrap, which is because it's a hard problem. But it is, in principle, one can do it. There is another kind of interesting bound from conformal collider, which is given by Hoffman and Maldacena, and it has been proved later by various people. But it's in a ratio of about A and C coefficients, which reads the lower bound over A over C is saturated by the free scalar, and the upper bound is saturated by the free vectors. But again, we can use this kind of bound if we can find some kind of bound on the A anomaly and combine this with this, then we can able to kind of find some kind of naive bound for the C anomaly as well. So this is one of the project we put up last year. Like we can probe these A anomaly coefficients, and then we can use this kind of like a conformal collider bound to kind of give some naive bound on the C anomaly. And then obviously the motivation is that can we directly do this bound on the C anomaly in terms of something. So let me take some time to review a bit what we did when we derive some bound on the A anomaly coefficient. To do that, we basically use the proposal of Komorgowski and Swimmer. What we studied, we considered that there is suppose some UV CFT, and we deformed by some relevant deformation. And it flows, and suppose there is some IR fixed point, but the IRs, like we consider only the massive QFTs, so that the IR CFT is really empty. And the QFT in between is given by a single stable massive G2 odd scalar particle. Okay, so we consider a G2 invariant QFT, which has a single massive scalar, like stable scalar with which is G2 odd. And then what we use is that now we want to probe this UV CFT A anomaly coefficient, and to do that, what we do is that we use Komorgowski-Swimmer prescription to replace all the mass scale of the relevant deformation. We just scale it by some another background field, which we call, say, dilaton, in the way that we scale all the mass parameters by mi times omega, and omega is omega under Weyl transformation, transform as e to the power minus sigma times omega. So basically, this relevant deformation deforms our UV-CFT, and we can compensate this deformation by introducing a new field called omega, which is a background field as well, and which has a transformation so that we can restore at classical level the conformal invariance. And then when we do this like RG flow, we integrate out all the massive degrees of freedom. In general, in the IR, we can get also a EFT action for this dilaton field. And then using Komogorski-Swimmer, one can see like how the 4 dilaton scattering amplitude behaves if we use this kind of parameterization for the dilaton, which is like omega is 1 over minus phi over 2 f, and if we take f going to infinity, which is like a probe limit, and in the probe limit, we can see that the 4 dilaton amplitude behaves like a UV times s square plus t square plus u square.
Question. Here are you also giving a kinetic term to omega?
Here, you like to define amplitude, one needs to give a kinetic term for omega, and one can give really a kinetic term so that the equation of motion is box omega equal to 0. And this also kills some part of the invariant part of the EFT action, which I will possibly describe if you ask later. Yeah. But it's not, okay, it's fine. Let me not make any comment. So, anyway. Then basically in the S matrix bootstrap setup, we consider basically scattering of these scalar stable massive particles, 4 particles, and then 2 scalar and 2 dilaton. So these are like the scalar particles, and the dotted lines are dilatons. And we use this as numerical S matrix bootstrap program to really find some
So I have a question. So do we know of any CFT whose A is smaller than that of the free scalar?
No, we don't know any CFTs. Yeah. It's unfortunate that we don't know, but what we see is that in the harmonic space, like of this amplitude and scalar amplitude, this lies in the, like, for example, so I think what I wanted to say is that, you know, like this strength of the 4 scalar scattering amplitude is bounded from this matrix bootstrap by some lower bound. It's minus, yeah, I don't now remember, 6.8 and some 2.7 or something, 2.6 or 7. And it happens that
Sorry, lambda, I forgot about lambda. What is lambda? I forgot.
oh, lambda is like in crossing symmetric point, if you have this 4, like this, take this amplitude, and in the crossing symmetric point, when S and T and U all are, S, T and U all are like 4 and at this crossing symmetric point, like this matrix bootstrap gives some bound for 4 scalar amplitudes, some lower bound which is forward, and what happens is that near this lower bound, we find that this is anomaly, we find the minimum of this anomaly value, and it is 0.32. So we know that it is matrix, but we don't know what the theory it corresponds to. And this is where we get this from.
But sorry to belabor on this. Do you expect that it is because we are missing some interacting CFT with a very small value of the A anomaly, or, okay, I mean, this is a bound, but practically it doesn't say as much because there's probably not a CFT with such a low value of A.
Yeah, we don't know like any such kind of interacting CFTs with such lower values of A, but this is just asymmetric bootstrap program basically keeps this one.
Thanks.
I also have a question. So you said that you assume that there is a single stable massive Z2 scalar particle. So if there were more than one, would it make your bound stronger or weaker?
It will make our bound really weaker. And this is, like, I think last week there is a paper by our student Jan Marucha, who has also collaborated in our this project, and he considered like he limited this due to invariance and considered also multiple particles, and he found that these bounds actually, like even for, yeah, if I remember, if there is no Z2 symmetry, he has bound this thing is like 0.15 times AP, and then it also goes down if you include multiple scalars, stable scalars.
Okay. I also have a comment about your list of available bounds on C. Of course, there is one bound which you forgot, which comes not from the 4-point function of the stress tensor, but from the 4-point function of any scalar field in the theory. So you can, if you assume that that your theory has a scalar field, well, in fact, any other operator except for the stress tensor, which is typically going to be the case, then it has been done in the early days of the numerical bootstrap by our group and also by David Simmons-Duffin and David Poland, that you can put an upper bound on the P coefficient of the stress tensor, which translates into the lower bound on the C. In that case, so you have some lower bound, which numerical lower bound. So if you're making a list as a matter of principle of all possible bounds, so then you have a concrete bound.
Yeah, that would be interesting.
Sorry, just to make sure I understood. So the claim is that this lower bound on the A anomaly is saturated by the QFT that saturates that lower bound on lambda. So the claim is that it comes from some UV CFT with that A?
Yeah, like
Okay.
assume that this QFT comes from some UV CFT with relevant deformation, and this will be the bound.
Okay, thanks.
Now, obviously, if we try to nicely
But can I ask a question? So here you are doing a semantics bootstrap analysis. There you keep this particle which really exists, and you add this dilaton which just probes the trace of the stress tensor. Right. But clearly this is not the most sophisticated analysis I could imagine, because instead of probing the trace of the stress tensor, you could just probe the full stress tensor. You could just, instead of considering this scattering amplitude, you could just consider sort of form factor where there would be two stress tensor insertions and this massive particle. So this would clearly give more, we will be putting more information, so it would lead to a stronger bound, presumably.
That's actually a good point.
Why can't you do this?
Yeah, so we can actually do it by, okay, let me try to think. So, yeah, what we can do is that we can also probe this A anomaly by scattering two gravitons and two dilatons.
Just don't scatter anything. Consider the correlation function of two stress tensors in presence of these massive particles.
Okay.
That would be the most constraining analysis. You would be considering one scattering amplitude, the one on the left, and then the things
Here,
on the
with
center,
with
you
these
would
are just the
replace
stress
phi's by the correlation functions of the stress tensor, and on the right, you would be considering a 4-point function of the stress tensor.
Right.
So why can't you do this? This would be more constraining. Is there some technical difficulty to do this? Why this dilaton? Okay, I mean, why should we care about the dilaton? Dilaton is just some very small part of the information.
Exactly. So dilaton is like introduced to really probe a combination of stress tensor from where we can read of this A anomaly like very simple way. Otherwise, you have to like take care of with all the tensor structures of 4-point stress tensor. So it's just a simple tool to probe a combination of the stress tensor correlators, so that just a scalar like part which contains this A anomaly. This is kind of a trick. You should know.
It's a trick, but since you're throwing out information, I mean, it's not surprising that your bound is weaker than the most optimal one. Don't you think so?
Yeah. Yeah, in a sense, our amplitudes also find some amplitude which saturates this bound. So.
Okay.
Okay. Yeah, I don't have a kind of nice answer to it, but yeah. Okay. So let me try to consider the setup once again, where we have some.
Just to continue, so you have an amplitude which saturates it, but you also have an amplitude involving the two dilatons, right? Which corresponding amplitudes, right? There's no guarantee that those amplitudes involving dilatons can be lifted to actual 4-point function of the stress tensor. That is something which we don't know. It might be that the dilaton amplitude exists, which saturates the bound, but actually there is no corresponding 4-point function of the stress tensor.
Yeah, but
I'm just saying that, Komargovsky-Schwimmer could tap this to prove a very concrete result that A is monotonic. But as long as you don't interested just in inequalities, but you want a quantitative analysis,
but this
there's no guarantee that that's the most constraining, very observable to consider. It's just one of infinitely many other observables to consider.
I agree, but in a sense, like you see, like here we are probing really quantum field theory, like off-critically, right? And there, if we try to study like 4-point stress tensors, right, it's really hard. Like there will be a lot of tensor structure in a QFT, right? And this gives just a simple tool to probe that off-critically, if we can also see how the anomaly changes. Possibly in a CFT, it's a good idea, working only in terms of stress tensor, but maybe this is a nice trick in QFT. Maybe Dennis has a comment to make.
I'll just make a very simple comment. In principle, including 2, 3, and 4-point functions in a QFT analysis and studying positivity constraints would be amazing. The problem is studying 3 and 4-point functions is very difficult. With Joao, we did 2-point functions of the stress tensor, and they are okay because you can do Fourier transform, you get spectral densities, they are real functions, very simple. But as soon as we go to 3 or 4-point functions, not much is known. So I agree with you, that would be amazing, but we don't even know where to start. Yeah. That's the current state of our understanding.
Okay. So let me describe this setup in a more detail. So suppose we have some UV-CFT. It's not necessary to have an action for it, but just for the sake of argument, let's consider there is some UV-CFT action, and we deformed it by a set of relevant operators. Okay, and this operator has the scaling dimension, which is 4 minus delta. Sorry. Has scaling dimension delta, which is less than 4. Okay, so this is a relevant operator, and we deform this thing. So if we deform by this deformation action, then obviously we are breaking the classical conformal while invariance. And So basically, we can restore this classical while invariance by introducing this prescriptions, which I was telling, like introduce another field, which is like kind of a spurion, and by replacing mi to be mi times omega with the transformation that omega goes like e to the power minus sigma times omega. Right? And in that way, we restore this classical conformal invariance, and then we can float, like suppose there is some IR fixed point and which is described by a CFT. But now, in presence of this like dilaton, obviously it will be like if we integrate out all the massive degrees of freedom, it is given by some EFT action, and this EFT action will contain obviously the part of the IR CFT action, which if we don't include this dilaton, it basically flows to some IR CFT action. But now there will be also interactions between these dilatons and this IR CFT degrees of freedom, as well as there will be completely some EFT action for the dilaton. So in general, this IR is given by some IR CFT action. Suppose the degrees of freedom now psi in curved background plus some EFT action for my probe fields or the background fields, and there will be some interactions also involving like the probe fields as well as the CFT degrees of freedom. Okay. So before going to talk about this complicated setup, let me first try to describe the simple one, where suppose I don't have any IR CFT degrees of freedom, so it's some gapped QFT, and only I started with this action and integrated out the massive degrees of freedom, and then in the IR I will have only EFT action. So this is the case 1. In that case, we will always have the EFT action, which is local in terms of the background field, because I only have massive degrees of freedom and I integrated it out. And just if I use now the anomaly matching condition, then I have to satisfy that this EFT action should contains the UV anomaly coefficients. And then one can use this OS-Jubino kind of procedure to find really the EFT action for like generating this thing as a generating this or generalizing this to finite Weyl transformation form. And this invariant part reads plus some irrelevant terms. Okay. So you can easily check that if you vary this, okay, so let me also give under while transformation, since omega goes like e to the power minus sigma times omega, and if we use this definition omega is e to the power minus tau, then we can easily see that under while transformation tau varies like tau plus sigma. And if you now, you can check that under this, under the variation of this part, one can get the correct anomaly equation. Okay?
Sorry, Viswajit.
Let me also describe the invariant part, yeah.
Sorry, can you remind us, there's no kinetic term for tau? There was some issue with r squared.
Right, so
giving rise to
I'm
higher
going to describe here,
Okay.
yeah.
All right, thank
So
you.
then one can write, obviously some while invariant part using just the metric e to the power minus 2 tau times g mu nu, and you can see this metric it combined a part of the while, combine a part of the dilaton and the graviton, and it is invariant under while transformation. So you can write a general form of the action which is out of this metric g hat mu nu, which is while invariant. And this capital lambda is basically, you can think of it just the lowest massive particle you integrated out along the RG flow. So this EFT action is valid only below this scale capital lambda. And now I am coming back to end this question, there is a term which is this r hat, and it's a two derivative order term, and this basically in general produce the kinetic term for the dilaton. Okay, and basically if you try to vary this dilaton action to get an equation of motion, that basically exactly gives this equation of motion which I used, when I was trying to tell about this scattering amplitude for 4 dilaton.
So here you include this lambda squared to make the dimensions work.
Yes.
If that was 0, then the kinetic term for the dilaton would be a 4 derivative kinetic term, right?
Right, but it turns out that, in examples, when you work out that it is non-zero, one can find these coefficients, if one, and it's really non-zero. In general EFT, when you do some integration over massive particles, it is present. Okay, if this is not present, but then you can try to think, see, our probes are really, we introduced by ourselves, and it's some trick, and it's some non-dynamical background. So we can add whatever for the probe we can, and we can add by hand some kinetic term for the probe as well to make, so that I get this equation of motion box of omega equal to 0. So it's a probe, so it's in our hand. So,
but there wouldn't be an issue with unitarity if you had some higher derivative kinetic term for this scalar. You could fix it just by adding something.
Yeah, we can just fix by a 2 derivative term by hand, because this is some kind of probe field which we introduced, and it's we can give a kinetic term by hand. And we can give it both in the UV and IR, and in the anomaly matching, if we give a free kinetic term, anyway, this is a free scalar, so it will be subtracted both from a UV and IR, so it will be 0. Anomaly matching condition won't be affected.
Thanks.
Yeah.
Can I also ask something
Sure.
more naive? If we are, I don't know, in a gauge theory where delta is classically equal to 4, does this trick is also useful? Does it also work?
If delta is equal to 4?
Yeah, classically.
Yeah, if delta is equal to 4, it is a bit subtle, for exactly marginal operator deformation. And there is some problems also with this anomaly matching conditions for exactly marginal, and there are some counter examples by Eli Pomini's group. So that's why I'm restricting myself to exactly relevant operator.
Thanks.
Yeah.
Yeah, I also agree. What this discussion about the dilaton equation of motion, why is this important at all? Dilaton is a probe. There is no dilaton actual theory. So I don't understand why you're saying if we want to think of it, we can think of it as a probe. It is a probe. There's no real dilaton.
It is a probe.
And since it is a probe, why it doesn't propagate? So why should we care about its equation of motion?
Yeah, it's
just a trick. I mean, it's just a trick to project on certain correlation functions of the trace of the stress tensor.
Good.
So why should we care about its equation of motion?
Okay, why Komargowski and Swimmer cared about it? Because they want to find a scattering amplitude of the 4 dilaton, right? And if we don't put this kind of equation of motion, then you can see these coefficients also will affect this A anomaly coefficient at 4 derivative order to the 4 dilaton amplitude, and it can spoil. So it's a trick to really remove the kinetic term for the dilaton.
This dilaton, does it propagate or does it not propagate?
It's a background field, it does not propagate.
So why then its equation of motion matters?
Yeah, it just gives the kinematic cons. It's in our hand, and we can add whatever we like, right? So we just want to analyze this part, so just we use that the kinetic term for the dilaton, so that we can kill this part for on cell. It's just a simple for simplicity. Yeah.
Well, imposing book cycle to 0 is equivalent for me to say I'm looking at correlation functions of the stress tensor on restricted to p squared equals 0.
Right.
Okay. Okay, then there's no parallel. Okay.
Yeah. Yeah.
Fine. Thanks.
Okay. Let me see my time. Okay. So now if you look at this equation and try to see where this C anomaly coefficient appears, and you can see this C anomaly coefficient really appears with the as a coefficient of this action. And this action, you can see it contains like tau times y square. So if we now try to expand this action about flat background, then you can see if we want to probe this C anomaly, the first simplest thing to probe it is by using like 1 dilaton and 2 graviton vertex. Okay. Obviously, you can also probe it using this like relation with omega and phi, also using 2 dilaton and 2 graviton amplitude as well. And that will be useful if you try to bound some A anomaly coefficient using the unitarity of the amplitude. But for a moment, since we don't really do yet the bootstrap for the to find any bound of the C anomaly, we are now just kind of probing. So the simplest thing to probe the C anomaly is basically using 1 dilaton and 2 graviton amplitude. And we can compute starting with this action, and you can see it will mix up, the vertex, which is the off-cell vertex. So it will mix up both with the A anomaly and as well as with the, at 4th derivative order, the coefficient R1. And if we try to just read off this vertex, starting from this action, it has like 3 tensor structures with some scalar functions built out of the momentas. And they have at 4th derivative order, you can see this coefficient contains both the information about, so here you should think really, since the AIR is 0 and CIR is 0, so this coefficient you should really think as just AUV and CUV. And you can see they basically mix up, but there are enough tensor structures, and we can able to isolate the C anomaly if we compute this vertex starting from some starting from the UV-CFT and some deformation. And then we can test whether this proposal works for some simple examples where the IR where the IR CFT is empty, and these examples are basically free scalar and free fermions. So I'll just briefly mention how to do it. So basically, you start with the free scalar action, conformally coupled. So I'm working in D dimension because free scalar in D dimension, it's also a CFT. So, and I will use dimensional regularization, which will be easy to handle these Feynman diagrams. So this term is important to conformally couple this free scalar in curved background. Then we deformed this theory by a mass deformation. Then we use this Komorowski swimmer to introduce dilaton, basically to compensate this deformation by introducing the dilaton field. So this is kind of our QFT action, compensate it. Okay. So we will start with this action and basically then compute like 2 graviton and 1 dilaton vertex. And do a low momentum expansion and try to read off the 4 power of momentum piece and compare with these tensor structures or with the prediction. And if we do that, we can easily find out these coefficients for the A, C, and R, or we can isolate them. Seven 760 pi square. CUV is 3 times AUV, and we can also compute some theory-independent parts, this R1, R0, all these coefficients, if we look the 2 derivative part to rid of R0 and the 4 derivative part to R1 also. Okay. Similarly, we can do for the free fermions as well. And free fermion is also, we can do in dimensional regularization because it's while invariant the action in any dimension. And here, let me write directly the action, compensated action. So A are basically the tangent space indices, and this is E A mu is the inverse Bielbein, and there is a covariant derivative acting on it, and then we have a mass deformation, then a compensation, and this psi of x, and this d mu of psi is just given by del mu of psi plus half times spin connection, and the commutation of the gamma matrices. Okay, and we can use this action again to compute like the one loop amplitude, one loop vertices, which relates to 2 gravitons and 1 dilaton, and there we have basically 3 diagrams. These are the charge arrows and 2 triangle diagrams. So let me put 1, 2, 3, and the charge arrow running in the opposite direction. And again, we can evaluate these diagrams and do a low momentum expansion, read of the 4 power of momentum piece, compare with our prediction, and we can read of the anomaly coefficients as well as the R1, and which agrees with the computations already people did earlier. These values are known.
Sorry, I think I got distracted a little bit. So
Sure.
we have just a free scalar, and we want to compute for a free scalar,
Yes.
and we define by a mass.
We deform by a mass term.
So it becomes empty in the UV,
Right.
in the IR,
right?
in the IR,
Then
and
we compensate by scaling mass to be mass times omega, and then this is the trick. And then we compute a amplitude in the IR, right? And do a low momentum limit, like all these momentas, ki square is much less than m square, and this is the IR expansion.
yeah. So you are just checking things that you know, right? You are just checking that if you do this expansion,
Right.
of the amplitude, that you get the expected A and C for a free scalar.
Yeah.
And of
Yeah,
course,
but-
it had to work, and it works. I'm a bit confused. Why are we doing this computation?
Oh, because actually, like in literature, like at the beginning, there are some confusions whether this C anomaly will match, because C anomaly is not monotonic. It will It's just to check that the C anomaly matches even for gap theories, and that was the motivation to cross-check at least for the non-example case ones.
So can you explain what could have failed? I'm a bit confused.
Like would have held that suppose if we started with this trick and compute suppose this set of like diagrams and do a low momentum expansion, and we found suppose the wrong answers for these coefficients, or not even compatible with the prediction of the vertex I have.
What would it mean? What would it mean if you did not get this result? If you had gotten something else, what would you have concluded?
So I would have concluded that using this kind of trick and writing down this EFT action for the C anomaly part and the other part is not working.
No, but how could it not be working? It's effective field theory. I mean, what could be?
Matching condition to write this EFT action, right? So this equation is basically telling that the UV and IR anomaly matching is holding. So the IR EFT action anomaly should match with the UV. So So if I don't get this thing, then I will have this kind of problem that causes this C coefficient won't match in the IR using this tree. But it's possibly not really kind of very deep, that possibly it will match, but there are counter examples where actually things don't match, like for some spontaneous symmetry case with some exactly marginal operator deformation.
No, I think you are completely right that sociologically there is this prejudice that A anomalies match and B anomalies don't. But I think you gave an argument that both must match, right? So it's great to check it, but I'm a bit confused indeed by this sociology of why people say that the B anomalies don't match.
I can make a comment. So there's one important statement or axiom needed to write the EFT action Biswajit gave, is the matching of the Weil anomaly. And matching of the Weil anomaly. So in order to write the effective field theory action, this thing, it is important to assume that the Weil anomaly is matched along the flow, so it becomes invariant. This is, if you think about it, it seems to be an obvious statement. What can go wrong, as you say, but sociologically, many people doubted it. Right, this is one thing. Second thing, there's a paper by Eli Pomoni et al. Who do seem to do the same analysis, and they get a mismatch. Right. Well,
that will always become irrelevant. So the only relevant operators which are important for this invariant part of the action will have this kind of form. All the operators with scaling dimension between 1 and 2 lambda that we remind is the UV cutoff for the IR EFT. I have this O hat of delta of x, which is defined as e to the power tau, delta tau. times the CFT primary, and G hat I already defined earlier. So this is kind of a while invariant combination of all. Now this, and also obviously there will be irrelevant terms. Okay? Which basically contains negative power of this capital lambda. Now we can try to see like if this kind of interaction terms appears like which basically contains some which basically couples this delay tone as well with the CFT degrees of freedom, can it affect our vertex? But what happens is that for generic delta, for 1 less than equal to delta less than 2, it turns out that it affects our vertex like for like 2 graviton 1 dilaton vertex, but only non-locally. It contains some like non-integer power of the derivatives or non-integer power of momenta. So if we are only interested about to read of the local part of the vertex, then we can really forget about the operators within the scaling dimension between 1 and 2. But it is important to consider the dimension 2 operator because it really can contribute to 4 derivative order. And if we do that and try to really suppose compute some kind of even like this kind of vertex, so in general, in presence of this, we will get a correction to the EFT action. And let me write down the EFT action correction.
Delta equals 1 also produce a local term?
Yeah, it produces like some 1 over box, some R hat and some R hat kind of term for delta equal to 1. And in general, it can contribute to some local part, but it is a 2 derivative order and we are looking at only the 4 derivative part, so we can forget about this. So for delta equal to 2, one can compute it, and in a covariant form it looks like so one should really think this expression as like as an expansion about the flat metric. And the important thing is that like there is a UV divergence, and to regulate this we need to add some kind of counter term, and that introduce this renormalization scale mu. And depending on the scheme, you can see that this log mu square coefficient is really like 4 derivative order, and it's a local term. But you can see if you compare this with the action here, it only can affect this R1 coefficient. So it basically shifts this R1 to some R1 prime. But it won't affect this anomaly terms, delta A or delta C. And what happens is that, but still, like if it just change R1 to some R1 prime, again, like in presence, like this vertex is enough to isolate the delta and delta C from it. So even in presence of this interaction, like obviously there will be some non-local EFT action, but from the local part, we can always read off or always isolate this A anomaly and the C anomaly coefficient. And then you can test this proposal for a simple example. Okay, not simple. It's a weakly relevant RG flow. So just to remind you that since we have now a IR fixed point, and at the IR we have some non-trivial CFT, so now like anomaly matching will tell us that these coefficients are not the UV coefficients, but these are basically difference of the UV and IR coefficients. Okay. Okay, so I think I have to go a bit fast now. But what we do is that we have some UV CFT, and we deform it by some like weakly relevant deformation at some scale m0. So this is the deformed action, and at scale, like if we just use a Wilsonian picture, and at scale mu, if we try to do renormalize, it will become some renormalized coupling and some renormalized operator. This is the CFT operator with scaling dimension delta is 4 minus delta, with delta is much less than 1, greater than 0. So it will like start a RG flow which is very short from UV to IR. Right, and what happens is that if one computes the beta function corresponding to this renormalized coupling, yeah, it has been discussed by many speakers in this conference. So it is given by the operator like OPE coefficients or related to the operator O with some sphere, like three-dimensional sphere volume times renormalized coupling plus order lambda cube, and one can also compute some anomalous dimension, like starting with basically the wave function renormalization of this operator. Which turns out to be just the derivative of the beta function with respect to coupling, lambda. And then the goal is to obviously find what is the change of the C anomaly coefficient. To do that, we already mentioned that in a CFT, okay, let me try to also give a bit more. Like the IR fixed point is given by some coupling lambda star, which the beta function vanishes, and the coupling at the IR fixed point is given by 2 delta times the OP coefficient COO omega 3, and as you can see, since delta is much less than 1, so obviously the IR, like the coupling at the IR fixed point is also small, so it's like start from a coupling 0 to lambda star, and it's a short RG flow, and we can use perturbation theory because it's a small coupling at the IR fixed point to study the full RG flow. So first, what we want to do is basically, since we know in a UVCFT, the C anomaly contains in the 2-point function. So this is a direct computation. We are not kind of probing by dilatons or anything. We just want to compute this object at IRCFT. And yeah, this is what I learned from Slava actually last week, is that since this test tensor won't receive any kind of anomalous dimension correction, so basically if we try to do like solve the Kalan-Simonyi equation, this resummation part of this RG equation won't give any kind of contribution. So basically because this resummation part is like, this is some running coupling at mu, the energy scale mu, distance between, so x1, 2 is given by R. This is the stress, if the stress tensor has some kind of anomalous dimension, then the expression would be this, but since the stress tensor don't have anomalous dimension, we would want to end up to consider this. So this resummation factor really gives 1 because this is 0 for stress tensor. And then one can, so basically then, since the resummation won't contribute anything, so basically we can use conformal perturbation theory to find the correction to it and evaluate this correction at the IR fixed point. And that would be enough to see at leading order in small delta expansion to get the correction to the C anomaly coefficient.
You might want to summarize.
Yeah, I need 5 minutes more, I think. Okay. So basically what happens is that if we want to compute this, so I'm now becoming a bit schematic, so basically it turns out that and basically one have to really evaluate this PTO correlator using conformal perturbation theory, and it's enough to evaluate at like IR fixed point, and then basically this contains the CT at UV, this contains the CT at, so CT at IR and CT at UV, and the difference we can find just evaluating this integral. And one can do this integral, and by direct computation we found that this delta C is given by pi square over this OP coefficient appears in the CTTO, and it's linear in delta plus some order delta square correction which we can evaluate. Now obviously the next step will be, can we reproduce this result using our kind of procedure of probing by dilatons and computing the two graviton, one dilaton vertex. So So basically to do that, what we have to do is basically we have to replace this mass scale. Let me try to see here. Here, this is a deformed action at scale mu, and so we have to write this. So we have some deformation action and we compensate it. So by and this is also like expanded about flat background, so this is some order kappa correction. And then also the UV CFT action. We can also expand about flat background, and we will have this flat background action plus at the order kappa given by the stress tensor of the CFT. Okay. And then we can use this deformation operator and with this action and try to compute like the EFT action at the IR by integrating out the CFT degrees of freedom. And it turns out that, let me write down the final result, like the important part which we need to compute for the EFT action turns out to be kappa square upon 2 square 2f. Okay, and first, like if we want to derive really the fourth derivative part, what we do is basically we replace this x2 to be like x1 plus x21, and similarly x3 to be x1 plus x31, and then we expand about small x21 and x31 to get the fourth derivative over the metric field. And by that way, basically, finally we have we are left with some kind of an action using transformational invariance, which we can evaluate, and finally we can break it in terms of some number of tensor structures with some kind of scalar integral, and we can perform this integral. And to do that, actually we have to use one trick, basically identify this mu with some scale involving this T operator, and this is not unique, and we found a nice scale to do that, which is, you can think of it like x1 2 square, x2 3 square plus, times x1 square or to the power 1 over 6. And using this kind of scale, which is a nice choice, we can perform this integral and can read off the fourth derivative part. And what we found is that obviously this scale is not kind of the unique one. So then if we do that, we compute this kind of vertex from this EFT and what we found is that from the coefficient of x2 and x3, we can uniquely isolate this like delta C result what we computed directly. But there is a problem actually till now, like for the first, like the coefficient of the tensor structure 1, and we can actually see that this, like we are not correctly getting the first tensor structure because this choice is breaking gauge invariance, and the gauge invariance breaking is just happening to the coefficient f1. So this is not yet a good kind of scale choice we find, but at least with this choice we can isolate this A and C from the two of the tensor structure f2 and f3, which are which has been produced correctly using this trick. Okay, so let me thank you.
Questions? But the conclusion here is that you are debugging the computation to find a small mistake, or?
Is that we understand how this kind of scale choice breaks the gauge invariance for the part f1, but it is not breaking the f2 and f3, and from there we can read out the delta C. But a nice thing would be that we should, if we can find some good choice which don't break the gauge invariance for all the three tensor structure, would have been nice, but we are a bit struggling with this. We have to fix it at some point. But the matching is working in a sense.
Yeah, so there's no contradiction because. Okay.
Can you explain why do you need to choose this scale? For example, when you do the calculation for the scalar, for the massive scalar, there you never had to talk to us about any scale choice or anything. What is different here that, I mean, the calculation is very similar. Also there you could have phrased your calculation in terms of, or is it not similar? So what's changed here compared to the previous calculation?
Comparing the previous calculation, what happens is that, like, if we start from this,
You probably asked what's the difference with the CFT computation before. There we had to evaluate the integral only once, and here we have to integrate twice the three-point function, and that introduces some IR divergences.
yeah, if you consider this to be a constant and evaluate this dx to dx to integral, it has in general some IR divergence. And to kill this IR divergence, one have to identify this in, like, in this way of computing. And in the other way of computing, starting from here, we have to solve a Galernian equation. And yeah, both has the same problem of identifying the scale. Is there any other question?
No. If not, let's thank Bijavit again. And